Hello, good morning, good afternoon. We start with the second module of our course, Power System Steady-State Analysis. So in this module, we are going to see how we can compute power flow in a systematic way. You probably have seen this kind of map. This is the electrical grid of Europe and the high voltage. Well, you can imagine that computing power flow through these lines are pretty complicated. It requires a lot of equations related with each node, related with each line, transform, etc. How we can automatize these kind of calculations. This is also the case of United States or even Russia. Those power grids are pretty complex. Well, in this lecture we are going to study how we compute power flows and how we can formulate them in a very systematic way. So let's start with some definition. Let's imagine that you have a network, in our case an electrical network. In networks typically we call edges to these parts, right? And nodes, well, to the stream of those edges. In power grid classify as at lines and buses. So bus is basically a node. We are going to assume like we have an injection. In general, if we have connected a generator or demand. Of course, if we have a generator, this injection is positive. If we have a demand, this injection will be negative. So nodal equations are the most common way of representing these power flow equations. They are referred to the nodes. We have to understand like these nodal equations should model that generation should supply the demand plus losses. The voltage magnitude should remain between some limits. We cannot have any voltage in each of these nodes. Generator can operate with some specific and relative limits. We cannot produce anything that we want with a generator, so they have some limitations. And transmission line also, they have some particular limitation depending on the capacity of this line. All the things must be considered when calculating this power flow. We recognize that this formulation is for a steady state, so we are not considering any kind of transient. We will see like the problem can be described as a non-linear system of equations. So we require some iterative process. Let's assume that we have a simple case of two-bus system. We have on the left bus A1. On the right we have the bus 2. I mentioned before that our standard now is to consider injection. So everything is injected and it could take a positive or negative value. So we are injecting in bus 1 energy, positive or negative. The current associated is I1 and the same for the bus 2. So let me modify a little bit the nomenclature with regard to the previous lecture. So for describing those phasors, in this case, sometimes you will see I'm using this V times some bar. So bar over variables is representing either a phasor or either a complex number. Then let me write what is the current with regard to the voltage. Instead of using impedance, I'm going to use admittance. So you see here that we have admittance, YS, this is related with the series admittance. And we have other two admittance, I call YG, sometimes is given by YG divided by 2. In this case we have two admittance, they are the same. So if we want to compute what is the impedance, we just need to make the inverse of the admittance. So then let's use Kirchhoff law to calculate what is the current with regard to the voltage. In that sense, I want to write a system of equations that it can do systematically. So let's start for doing the nodal balance at this point in red 1. So the current that entered here, I1, is equal to the current that is leaving through this shunt element. What the current here is equal to V1 YG. plus the current that is going in the series part. The current in this last part is equal to the voltage drop V1 minus V2 divided by the series impedance. I have admittance, so it's multiplied by the series admittance. Well, I see that the current depends only of the voltage in 1 and voltage in 2. And of course depends on the parameters of the line, which is given by this shunt admittance and this series admittance. I can work the same for the node 2, and then I can compute what is the current in 2 as a function of the voltage in 2 and voltage in 1. So I have a similar expression. So the next thing I want to do is just to write a matrix form of these two equations. So I just write my output vector, the vector of currents. Remember, every element is a complex number. So this matrix is a matrix of complex numbers. And then just multiply by the voltages. This is a linear product. And I just need to rearrange terms. So B1, I1 depends of B1 times YG, B1 times IS. This is in here. And also depends on minus B2 YS. This is YS. I can do the same for the other part. So if you see here, so we have a matrix, this matrix, which have, well, in this case 4 elements, of course. I will call each element like classical definition for a matrix. Y11 is the element of the first row and the first column. We can compile in a very compact form this equation, something like this, like I bus is equal to Y bus times B bus. Sometimes you will see something I will write like this, only like this. So I'm using these square brackets to represent a matrix. Each of these matrices is a matrix with complex numbers, and this is a linear system. Well, this can be also extended to calculate what are the complex power injected on each node. And you can imagine, like, power actually will be much more important for us. They are important because this is the thing that it is paid. So we usually pay for active power. So we will pretty be interested in understanding what is this active power. And most of the equation will be given in terms of power. For calculating power in node 1, again, this is injection power. So it's equal to this active power plus reactive power, this complex number. And remember, this is V times I star. Star representing this conjugate value of the current. And as I mentioned, this is a generic node or generic bus. So it means like I either have generation or demands, or maybe I have both of them. So I will represent this injection, this S1 is just the injection, as a positive in generation minus a negative demand. Well, I can still work with this equation of the complex power. So S1 is equal to V1 times I1. So I'm going to replace I1 by its definition. Remember, it was given by this matrix. Well, I just need to pick up the elements for the particular column of V1 and I1. So I'm getting those elements, I11 and IY2 times V1 and V2. And I can do the same thing for V2. So here there is one important observation. If you see here, either S1 and S2 complex power depends only on the characteristic of the lines. This is my network, and the voltages. Thus, if the network doesn't change, that usually doesn't change, I can say like the power will be a function of the phasor voltage. And this is important because we can say that those voltages, phasor voltages, they are representing the state of the system. What is the meaning of that? So if I know what are the voltages, phase voltages means like magnitude and phase angle, I will know the power injection at every node. And also, in going back, I will know what are the currents at every node, because they only depend on voltages. So voltages will be playing a key role in power system for understanding what is happening in the power system. So you see like S2 is a multiplication. Now this is not linear anymore. And how we can perform this multiplication? Well, those are complex numbers, so we can use definition of a complex number in two forms, rectangular form or polar form. If I'm using polar form like this for both complex number or both types of complex number that I have in the definition of the complex power, it will be easy to compute or to find what are the explicit formula for active and reactive power at every node. So this is just a formula, but this is basically coming for this matricial form. So the power, the nodal power vector is equal to voltage times Y times voltage. Here delta I and delta K is representing the phase angle of voltage elements, and theta IK is representing this complex number in a polar form. If I'm using Euler identity, I can have some explicit formula for active power and reactive power. So in this formula, I have, this is just values, this is value, this is the module, and this is cosine, and those are phase angle, and this is the angle related with the element IK of the admittance matrix. If I'm giving you this matrix, of course the matrix is coming with the phase angle, and then I'm giving you voltages, you are able to compute for a large number of elements what are the active power and reactive power which is injected at each node. Simple. Well, another observation, this is a nonlinear equation. And typically we don't know voltages, but we probably know information about the injection power. We can know what is the demand of one node or what is the generation at each particular node. So let me come back to this Y matrix or Y bus. This admittance matrix has some special properties. So I recall the previous one for system of 2 by 2. So the matrix have a side of 2 by 2. I have two nodes, this matrix have a side of 2 by 2. So the first observation is, so what we have at every non-diagonal element of this Y matrix is the minus series admittance. So that's very simple. Now let's imagine that we have a system of 4 nodes. Node 1 is connected with node 2, node 2 is connected with node 3, node 3 is connected with node 4, and 1 is also connected with node 4. We have no connection between 1 and 3, and no connection between 2 and 4. So in those cases, there will be no elements in these non-diagonal elements of the matrix. Most of the grids are not fully interconnected between all the nodes. So it means like this matrix have a lot of non-diagonal elements that they are 0. So this is what I say here, this Y bus or this admittance matrix is sparse. It could be more than 90% of the element being 0. Then there is another observation. What I have in the diagonal elements is the sum of all admittance which is connected to this node. For example, in node number 1, it is connected this admittance plus this admittance. So I have sum of G1 and YS. Connected to this node, there is this admittance and this admittance. So I have YA and YS. So we can build in a very systematic way this matrix. Finally, I forgot to mention, but this matrix is symmetric. very good properties of this matrix. It's sparse and it's symmetric. So that's could bring some advantage of working with this matrix or formulation that involves this matrix, because we can exploit some numerical methods to take advantage of a sparse matrix. So we have been writing all these equations in this matricial form. I have this equivalence of the Ohm's law, and this is the equivalence of power equation. Those are very compact form, but you see like each of these elements is a matrix, and elements of each matrix or vectors are complex numbers. On the right hand side, you have the case of the admittance matrix for the Polish power systems. You see, while the diagonal, of course, have elements which are non-zero. Close to the diagonal, you have connection with the neighborhoods. So you see, like this matrix is pretty sparse. Only 0.11% of the elements are non-zero elements. Instead of using this polar form of the admittance matrix, I can use rectangular form. I will have some element related with the real part, and this is with the imaginary part of this admittance matrix. Ik, remember, is representing the values of the element I with regard to k. Still, this is nonlinear, so I have cosines, I have sines. How looks like this power flow? So those are very nonlinear equations, and it looks like this type of surface. On the left, you have a very simple case where you have only 3 power generated by one active power by generated by generator 2, and reactive power of the generator 2. So you have 3 elements that can vary in a very small system, and it looks like these very particular shapes. One observation is this is non-convex because, well, you already have 2 regions which they are separate. The same on the right hand side, you have again 3 other elements that can change, but you see those surfaces are challenges when we want to solve for large case studies. We will see later that this formulation of this AC power flow is typically simplified by other approaches. Let me give you an example. I would like to build what is the admittance matrix, this way bus. I'm giving you information about this 3-node system. I don't know what is connected at every node, but I know it has 3 nodes. There is 3 lines. Every node is connected with each other. We know like the shunt element is given by J 0.01. There is an assumption that we are using a pi model, like the one I mentioned before. And I have 2 of them. And there is a Syrian element, which is the impedance. In this case, I'm giving you the impedance. So I need to compute what is the Syrian's admittance. It is 1 over CL. So this is minus J10. Okay, so I can say I will draw here. So this is minus J10, minus J10, minus J10. In general, I don't need to draw that, so I will be able to build this in a very systematic way, even by computer, so I don't need even to have this scheme of the grid. Okay, let me write also what are the shunt elements. So shunt elements, so I have a pi model for this first line. I have another pi model for this line, and I have this pi model. And then I need to give numbers. I will call this 1, I will call this one 2, and the last one node 3. Okay, now I'm ready to build the Y matrix. So this Y matrix is equal to, let me start with the shunt element. I will divide the matrix like this. Okay, I know the matrix is 3 times 3 because I have 3 elements. And then I can start to complete the elements of the diagonal. So let me start with the element which is connecting node 1 to node 2. It is this line. Okay, this is minus the value of the admittance. then is J10. Well, this Y is symmetric, so I can fill the element to 1. Between 1 and 3, I have the same. Everything is symmetric, so I just need to write J10. And this is symmetric, this is J10. And between 2 and 3, again, we have the same series impedance. This is J10, and this is J10. Okay, next thing is to compute what are the diagonal elements. Remember, in the diagonal element, we have to sum up all the elements that are connected to this node. For instance, in node 1, I have connected one of these shunt element. I have this other shunt element. I have this series, and then I have this other series. I will have y11 will be equal to minus J10. This is multiplied by 2 because I have 2 of this element. Plus, I have 2 shunt elements, and those shunt elements are J0.01. Remember, this is a complex number. So I have those of these 2 of this element, then I need to multiply by 2. So by doing that, so we have minus J1998. So this is minus J1998. And I have the same for other elements because that is symmetric. Yes, very simple. So no matter how big is the grid, this admittance matrix construction can be systematized pretty easy. I have shown you different ways of writing this equation where I have injection, active, reactive equal to some equation that depends on the module of the voltages and the phase angle for both cases. So I can say, like, for every node I can have these 2 equations. This is 2 equations that if I multiply by n number of nodes, I have 2 times n equations. But in principle, voltage angle, voltage magnitude can have any value. In principle, I don't know them. The same for power injections. Maybe they are not known. So how we can calculate 4n variables having 2n equation? For doing so, we need to fix 2 variables at each node. Then we will have 2n number of equations and 2n number of unknowns or variables. That will be our goal. How we can fix at every node 2 of those variables, right? Among all these 4, I need to fix only 2. Then I will have another 2 that will remain unknown and will be given by the set of equations that I have in each node. So how we are defining which of those variables should be fixed? Power engineers basically classify nodes depending on what they know from each node. So there is a classification of 3 types of nodes. The first class of bus is known as a PQ bus. And PQ bus means, like, we know active and reactive power injection. So knowing what is the active and reactive power injection means we know demand, either if we have or maybe don't have, and generation, either if we have or maybe don't have. I say here power J specified because we will see this power can be changed, but for our goal in this module, this power is given in PQ buses. If we know P and Q, so we don't know V and delta. The other type of nodes are the PV buses. Well, PV buses are buses where we know active power of demand, reactive power of demand, so typically demand is always known. Then we know active generated power, so it means like we will know what is the active power injection. And voltage is specified. Typically these PV buses are buses they are doing some voltage regulation. This is why this is specified. So engineers say, well, we'll keep this bus at this voltage and then we will have some kind of control so this doesn't change the voltage. So what is unknown in here? The total injection of reactive power and the phase angle. And the last classification is for the what is called reference bus or slack bus. This is selected only for one bus of the network. This will be used as a reference because if we observe power flow equations, this power equation depends on the difference of phase angle between nodes. So we have to fix one of these nodes to have a phase angle equal to 0. So this is what is called the slack bus. So in this particular bus, and there is only one, delta 1 is specified and voltage is specified. So the total power, active and reactive, is unknown. Well, with that, so we can start to write the power flow equations. So those variables who are unknowns on my system typically are control variables. So it could be power generation, it could be active power and reactive power, or some voltage. There are some other variables that are not controlled and typically are demands, active and reactive loads. As I mentioned before, voltage phasor is a state variable. So knowing the voltage phasor at every node, it gives us information of any other variables of my system which is in a steady state. Typically we have limits of the magnitude, so the voltage it have to be between some minimum and maximum limits. The difference of phase angles between two nodes also is between some maximum limit. Power generated have to be between some limits, so it cannot exceed the capacity of the generator, either in active or reactive power. And generators typically have some minimal active and reactive power, means like if I'm switching on a generator, the generator will be producing some minimum active and reactive power.